Hey everybody, it's Kyle, and I'm going to talk about part 3 of homework 4 for computational methods. In this part, we're going to implement a flash calculation function to calculate vapor and liquid compositions of a flash drum given a feed of 10 moles of ethanol and water at a temperature midway between the dew and bubble temperatures at a given pressure. So here we go. I'm going to start by just defining some of the constraints that we're given. So the pressure is going to be 101, 325, and it gives us molar feed rates. So our total number of moles is what we can start with. I'll call that NF. Or I guess we can leave this in component form. So NP array, and it's 10 of each. Alright, so then now if we want to break this down into a fraction, we can do ZF is equal to NF. Since we left NF as by component, we can have components of each fraction, which is nice. So NF divided by NP dot sum of NF. I don't know what. Oh, okay. I forgot to put parentheses from NP.array, it's a function. Alright, so there we go. So now if we take a look at our ZF, NF's pretty clear, it's just the array. So if we take a look at ZF, it's an array of our components. So we got that down, now we can come back here as well. And conveniently, we just made functions that give us the dew temperatures and the bubble temperatures, so we'll be putting those to use. So let's start with our dew temperature. So our dew temperature function takes in a mole fraction, which we will give it ZF, and a pressure, which we're given as flash P. So now we'll have our dew temperature. And if we remember, so dew temperature, we actually output the mole fractions as well as the temperature. So an easy way to store just the temperature, which is what we want here, is to, we want the second term, which is the temperature. So if we put a little 1 there, we'll be left with just the temperature. And then bubble temperature, I did this one a while ago. Let's see, what did we call it? Bubble T. And that one just returns the temperature. So it doesn't, like if we take a look at the dew one, yeah, we're returning 2 values here, where the bubble just returns the 1 temperature. So bubble T, and that again requires the mole fraction and flash pressure. And there we go, so now we have the bubble temperature and the dew point temperature. And I think it's specified that the temperature comes in midway between dew and bubble temperatures. So our actual flash temperature, so we'll call it flash T, is equal to, we're going to name these as variables, dew temp, and B temp. So our flash temperature is just the average, so NP dot average, which I think I normally use NP dot mean. I don't know if there would be a difference, but dew temp and B temp. So let's take a look at what our flash T is. 349, and yeah, that looks in the middle. It said 351. I believe it was 347 for the bubble temp. So yeah, that looks good. Looks good to me. Alright, so now we want to define a function that we're going to be solving to calculate our vapor and liquid compositions. So we'll call that function fugacity, and that's going to take in a vector v. It's going to be pretty similar to what we did for the dew temperature, where we're going to be using like a variable transformation in a way, but this time we're going to do it with exp it, and that's doing the same thing where it's changing our bounds on variable from 0 to 1 vertically, rather than a normal mole fraction, which is can only be from 0 to 1 the x direction. So yeah, so we'll be using the vector, and we'll just call it v again. And then what we're going to want to do is we're going to want to return, this was a long time ago, we're going to want to return Raoult's law solved for equaling 0, kind of like how we did it last time. And I think I have that typed somewhere, so yeah, we're going to do it the same way as this, so I can just bring this down using our matrix, what's it called, matrix vector multiplication method that we did in part 1. So bring that in here, and we're going to want to define some stuff that's going to be going in there. Alright, so we'll start with the moles. We have moles of feed going in, and we're going to vaporize some of it. So we're going to have a certain amount of moles of vapor. And like I said, we have our moles of feed, and we're going to have this percentage of how much is vaporized. So as I was discussing with the variable transformation that we're doing with exp it, that's what we're gonna be solving for. That's what we'll do here. So exp it v. So this is just our total moles coming in times our fraction that's going to be in vapor. And then obviously whatever's vaporized, whatever's not vaporized is going to remain in liquid. So the best way to show that is that the moles of liquid is equivalent to the moles of the feed minus the moles of the vapor. And then we can do our x, which is our liquid mole fraction, and that's obviously going to be equal to our moles of the liquid over our moles of total liquid, NP dot sum of the moles of liquid, and we'll do the same thing with our vapor, NB divided by the total number of liquid, of vapor moles, so sum NB. Alright, and there we go, I think. Good, got the spacing right. Alright, so now what we have to worry about now is we don't have a temperature and pressure defined yet. So this fugacity function that we're solving for, we're actually going to want this to be inside of an outer function that we feed our conditions to. So I think if I highlight all of this and bring it in, it's going to yell at me until I define another function out of it, and we'll just call that, I guess we'll call it flash. It's like our flash conditions, but it's mainly temperature and pressure. So flash temperature and pressure, and that's going to take in feed, a temperature and a pressure, which I said a T, but we know the T. It's our flash T and our flash P in our conditions. Cool. Alright, so now I have that outer function that satisfies our T and our P, our inner function, which actually returns the equation that we want to solve. And now we want to actually solve our equation. So we'll come out that inner function and we will do a root of our function, fugacity. And our initial guess, we can just guess that like 50% gets vaporized. So if we look at 50% here on our transformed variable, it's actually going to be at 0. So we just want to guess zeros. So we can just do NP at zeros. And I guess for now, since I know I have 3 components, I can just say NP at zeros of 3. Now, if you didn't know, or if you had more components or something like that, I believe we could just do nf dot size. I can check that if I come here. I mean, nf dot size, it should just equal 3. Yeah, so nf dot size is just our number of components coming in. So I'll actually leave that. It makes the code a little more general, which is always nice to not hard code stuff in. Alright, so yeah, we want the root of fugacity, and our initial guesses are the zeros. And like I ran into earlier, I want to store roots, always store the answer I want in that x variable, so I want to just do .x because that's what I want out. And then again, like earlier where we used q as our transform variable, our answers here are still in that transformed form. So we did that exp it, and we never brought it back. So I can actually, I think I can show this if I haven't returned it yet. Well, I could show it by printing that out or seeing what's going on here, but basically I'm going to need to bring it back to the form we want it in. So I'm going to say exp it again, and now I want to this is basically what I want. It's the percentages of the feeds that is vaporized. So if I want to bring that to just a number of moles, I can do this. So I want number of moles in the vapor, so that equals the percents. And then I can multiply by the number of moles of the feed. And there we go, which looks good. And now, let's see. I have number of moles in the vapor. I also want, yeah, so now I'll have number of moles in the vapor, so I want number of moles in the liquid as well. I want to calculate everything I want here, and then I can just return it all in one return with this outer function. So NL is the same as earlier. It's going to be equal to NF minus NV. Basically I want all this stuff, so I could have just done that easier. And there we go. So now x is equal to NL over NP, that's sum of NLs, y is equal to NV over NP, sum of NVs. Alright, so this gives me the moles in the vapor, moles in the liquid, mole fractions of the liquid, and mole fractions of the vapor. So I can return, and what do we want? What are we looking for? We are looking for the vapor and the liquid compositions of the flash drum. Alright, so that means we want X and Y. Vapor and liquid, so we'll do Y first. So I just want to return Y and X around that, and now it should be good to call on this function, flash TP. We'll feed it in our NF and our flash T for the temperature, and our flash P for the pressure. And yeah, here we go. So looks like our vapor phase is dominated by the methanol, which it has the highest mole fraction in the vapor, and this makes sense because methanol is the most volatile. Where our liquid phase is majority water, and that makes sense because that's our least volatile component in our mixture. So these answers make sense, which is good. Something else that is kind of interesting to calculate, you can show the percent of the feed that's vaporized, and that's pretty simple. It's just, and if we remember, NV, NL, and NF are still based on component, so if we want the total percent vaporized, we just do NP dot sum of our vapor, capitalizing that, of our vapor, divided by NP dot sum of our feed, and this will give us percent of the feed that's vaporized, and what I'll call that, it doesn't really matter, I can just return that, but vaporization. Then I can return vaporization, and it should come, yep, and it comes not as an array, just as a singular value now, since I did the sums divided by the total sum of moles, and it shows that about 64.2% of our feed is vaporized by our flash drum or flash calculation, and here's the percentages, like I said. So the vapor is majority methanol, and the liquid is majority water, and that's completes the flash calculation, as well as completing homework for our last computational methods homework. So it's been a great year. Thanks for watching.